This is the last slide we had before we split for lunch. And one thing I forgot to mention about this slide is this is a double logarithm plot. So both the y-axis as well as the x-axis are logarithms of those quantities. So that's why you see 0.1, 1, 10, hundreds, it goes in tens over there. Same thing on that scale as well. And while different materials have been plotted and clusters have been formed, you also see some dashed lines. So these dashed lines are where it's a straight line between these two quantities. That's essentially what we're talking about, where sigma t by E is a constant, just like this particular line. So you see those are parallel to those, which essentially means different values of this particular ratio sigma t by E, which is in essence, if for a brittle material, this is actually a measure of the elongation at which the failure takes place. Okay, so how much it can be stretched. So larger the sigma t by E, the larger elongation you could have up to failure, and typically some of those are good for impact resistance. But not only are sigma t by E lines plotted, but also you see a few other lines like sigma t squared by E, sigma t power 3 by 2 by E, etc., which cover various other aspects of safety. So beyond the scope of this course, so we'll not look at that. But one of the things that it distinguishes on either side of some of those lines is which of the failures will occur earlier. See, for most of the materials on this side, you will have the material failure occurring before the geometric failure. On the other hand, here you will have the geometric failure occurring before the material failure. So that's essentially what you're talking. Why? Because you see in this range, you see the Young's modulus is very low. So in other words, stiffness is very low. For the same stress, you'll have larger deflections. So the chances of geometric failure are much more over here. On the other hand, if you look at materials over there, what are you looking at? Very large Young's modulus, but very low failure strength. That's a tense in tension, right? So they essentially will be failing more in the because the material itself fails even before the geometry fails. So instability is not an issue to be worried about for materials in this end of the spectrum, or rather that corner of the spectrum. Okay. So I think it's more of a to understand the qualitative nature of the different kinds of materials that we talked about: metals, ceramics, polymers, and then combinations thereof of composites. So all of them you can see over there at that point in time when this chart was made. This is a chart which keeps getting updated depending upon the new materials that are discovered or innovatively manufactured using existing materials. Okay. So we are still answering that same question of what are composites. We already said they are made out of more than two materials, at least two materials, and we saw that those two main materials are the fiber and the matrix. So we took up the first of them, and we've started answering this question, why fiber. First of all, we defined what is a fiber geometry. We said that it's the cross-sectional dimension is small compared to the wavelength, but just being small is not enough because that's a rod as well. And then we said very small, and therefore we can talk about it in the form of what we call as the fiber, which is having essentially the bending stiffness approaching zero. Okay, in the limit the bending stiffness is approaching zero. So it's all relative sense. It's not exactly zero. It's negligible compared to the other stiffnesses that are there, in particular compared to the axial stiffness. But of course they are in different units, so you must use an appropriate way to compare them by introducing certain dimensionality, non-dimensional ratio of the two. So coming back to why fibers, let's ask ourselves a few questions within this question in order to understand the significance of this particular geometry, right? So first of all, let's answer a very simple, innocuous looking question. What is the material property? What do you understand when you say something is a material property? Of course, you know lots of examples of material properties like density, thermal conductivity, etc. So when you say a particular quantity is a material property, what does it mean? What does it imply to you?
Characterizes like how what it is or how it behaves, or
right. When you say it, you are referring to that particular material, right? Yeah. So essentially you're talking of, from the very name itself, a particular property of that material. So as you say, it characterizes that particular material. So more often than not determined experimentally, but there are theoretical ways also to determine some of the properties, right? So anything else when you say material property, what does it imply to you?
How it would react to certain outside factors, like forces or something.
Mm-hmm. Mm-hmm.
But also like just what it is without those forces.
Right, right. So it's essentially the very nature of that particular material. So essentially your anything else which is changed other than the material itself should not change it, right? So that's what you're saying is in terms of its inbuilt nature, right? Right. Yeah. So that's true. That's what we typically understand by a material property. So for example, if I were to make, let's say, an aircraft with a particular choice of material, let's say a very specific aluminum alloy, not any generic aluminum alloy, particular, let's say 2024 with a particular heat treatment, and then I make a boat also with it, with the same material. So whether it is part of the boat or whether it's part of the aircraft, that material property should not change, right? So if it's, let's say, the density of the material, whether it's the density of the material even after it has become a part of the aircraft, or even if it has become a part of the ship, it should remain the same, right? So that's our generic understanding of that. Or if I make two structures like these of the same material, then obviously that particular material property should not change, right? Or if it's the same kind of geometry, like a rectangular cross section almost, and then with curved edges. So, and I make this. So essentially these are both cuboidal kind of structures, just the size is changing. Between these two, the shape itself was changing. This is a circular cylinder kind of a geometry. This is a rectangular kind of a geometry. So whether I change the shape or I change, because these two might have reasonably the same cross-sectional area, approximately in terms of orders of magnitude at least. Now I'm talking of two which is having similar shapes but different cross-sectional areas. So either I can change the shape or I can change the size, or both simultaneously. But irrespective of what I do there, the material property should not change as long as I'm using that specific material property, right? So if that is the case, let's talk about this particular quantity. We gave already density as an example of a material property. Another material property that we have been studying is that sigma u, which is called as the uniaxial tensile strength, right? So in other words, you're applying load only in one direction. You're going on increasing that load to increase the stress, and that stress you're measuring at a particular value of that stress, the material fails, right? So that's a uniaxial tensile strength. Now, is that a material property or a geometric property? How many of you think it's a material property? The uniaxial tensile strength? Only you? 2, 3? Nafis, you don't think it's a material property?
Did you say it was sigma UTS?
Yeah, sigma u, what we've been using for the strength-based design, sigma u by rho.
Stress as well.
Yeah, so remember, how do you get to sigma u is you take a uniaxial testing machine, UTM, in which you fix one end of the specimen. The specimen itself is made to a particular dog bone shape, which is according to certain standards, ASTM standards. And then you start pulling the other end, you put strain gauges on that. You keep taking the readings of the load cell as well as the strain gauge. In order to measure the stresses, you measure the strains and then you plot them. So then it's a particular limit beyond which the material can't take anymore. That you call that uniaxial tensile strength, right? For some materials, it might be the first major phenomena which is occurring, but for some metals, you might find proportionality limit or yield, etc., occurring before that. Okay, so keeping that in mind, let's come back to you.
It's always in that dog bone shape. It's always measured.
Yeah. So the reason is that once we answer this particular question, things will become a little more clearer. But to answer your question, we just want to standardize certain things.
Right.
So we do not want things giving for the same material such different properties just because they tested it in a very different way, right? So the testing conditions should not affect it. So therefore, there are certain standards which are defined by entities like ASTM, so which will give you a particular shape. So the reason why that particular dog bone shape is because of the Saint Venant's principle that we've been discussing in the beginning, that at the boundaries, the way the boundary condition are applied and how the loads are applied will affect the stresses in a local region, which is of the same order of magnitude as the size of the cross section. So if this is one width, up to about one width, it will depend on exactly how I'm applying the load. Okay, but once you go to the interiors, it doesn't matter. The resultant is what matters. How you distribute that resultant does not matter, right? So that being the case, you make it a dog bone shape so that it's much larger for the grips of the UTM to take that, and in between in the dog bone there's a constant portion where you are actually measuring the strength, stress and the strain.
So since the geometry is always the same,
Mhm. Yeah. So because it's a material property, right? So it should not change, right? Yeah.
For some composites though, can it be also geometric property in a way? Like it's like for wood, for example.
For example, what?
For wood.
Wood. Yeah. Right.
The way the grain goes.
Right. No, so that's absolutely right. So what we are talking about here is the uniaxial tensile strength. So we are talking about in the case of the metal, it doesn't matter. But as you said, in the case of the composite, along the fiber, it will be much higher compared to perpendicular to the fiber or any other direction in between, right? In fact, we showed a plot also of Young's modulus, how it changes with the angle. The same thing holds for your sigma u also to some extent, right? So that is true. But right now, remember, we are not yet talking of the composite as a whole. We are talking only of the fiber, right? So we are talking of only the fiber, and at this stage, we just want to know its UTS. When we say it's only along the fiber direction, because the other directions, the UTS is very difficult to measure, because you have to take a fiber which is of the order of 10 microns and try to pull it apart this way. That's very difficult. To some extent, compressive tests are easily done, not as easily as the UTM tests, but there are ways to handle that at a small length scale, how you can compress and measure the strains and the stress, and then you get the stress strain plot all the way up to failure, right? But tension, it's kind of difficult, but there are workaround ways. Let's not complicate things right now. So we are only talking about, because we know that any other direction, anyway, this guy is not going to be of any use to us. The only use at fiber is if it is subjected to tension. So if that is the case, the UTS that we are talking about is a fiber along the fiber direction. Okay. So right now we are not even talking about fibers. We're generally saying, is the UTS itself a material property or a geometric property? But it's very good, Ivan, that you pointed out that aspect of it, that whenever there is anisotropy, that is a material is not isotropic, then to some extent there is geometry involved, because the direction in which you measure comes into picture, and direction is always a geometric feature. Yes. So anything else you would like to say? Is this, do you all unanimously agree that it's a material property? Yeah. Okay. So that means if you change the material, it should change. If you don't change the material, but you change either the shape or you change the size, keeping the shape the same, or you change both shape and size, that property should not change, right? Right? Because that's what we said when we said structures. We said it's made out of two aspects, the geometry and the material, and the geometry is made out of shape and size. So these shape and size are entirely geometric features. They are not material features. So if I'm keeping the material the same and change only the shape or size, obviously the material should not change. And if the material doesn't change, the material property should not change. Therefore, UTS should not change if it's a material property. That's essentially what we are trying to understand out of this, right? So now, do material properties, we're just trying to make this same question a little more intricate and trying to understand it in a better perspective. So do material properties, like for example the UTS that we just introduced, depend only on the chosen material or also on the shape and size of the object, which is what we said, because we classified shape and size as geometric features, not as material features. So therefore, the material property we think is, once the material is fixed, it gets fixed. It doesn't change with, as I showed you these three examples of changing the shape and or size, it should not change if it's all of them are made out of the same plastic, let's say. So then they should not change, right? So do you still agree with this? Yeah? right? So let me make it more specific, not generally talking about shape and size, but a particular aspect of the size, which is the fiber diameter. So I'm keeping the shape fixed. So it's all circular like this, circular cross section. Length is large, not just large because it's a fiber, it is very large compared to the breadth and the height, right? So it's the breadth, this is the height. In this case, it's circular geometry, so we just need to talk of a diameter. So L by D ratio, not lift to drag, but length to the diameter. So the length to diameter ratio is what we are talking about. So let's keep the length constant and start varying the fiber diameter, okay? So now this has a particular diameter, so about, let's say, 1 centimeter diameter it has. Now I want to change that diameter, right? But I want to change in the typical dimensions of the fiber diameters, which is of the order of a few microns. We saw it's typically of 10 microns or so, most commercial fibers. Some fibers like boron, etc., might be thicker because they're coated fibers, like silicon carbide also. But in that range, when you're so this is of the order of a centimeter, okay? Whereas in the range of microns, we are trying to vary this fiber diameter. So then should the ultimate tensile strength vary with the fiber diameter? Same material, I'm keeping the same material. Let's say carbon fiber. So I'm taking a bunch of carbon fibers, each manufactured with a different diameter or radius. So now I want to put each one of them into a UTS and try to pull it. So measure the stress strain and go all the way up to the failure stress, right? So will the UTS, that is the failure stress, depend upon the diameter of the fiber? No, right? Will the force depend on the force that I have to apply for failure? Will it depend on the diameter, right? Yeah. So it's obvious because the UTS is, as one of you mentioned already, it's a stress, but it's a stress in a limiting sense, right? So it's the maximum stress that particular material can take for tension in a particular direction, which is the direction we call as uniaxial, that axial direction. And so therefore that particular failure, whatever is happening, should be a material property. But if it's a load, then that load gets distributed over the cross-sectional area, and if I change the diameter, the cross-sectional area changes, and therefore the stress at which it fails might be constant, but the actual load at which it fails will depend on the area. So what do you think? More the area better or less the area better in terms of load it can take? Huh? Yeah, more area, because if the material property of UTS is the same and you're multiplying it by an area to get the force of failure, so at which failure occurs, so then obviously more the area, the more it is going to be. I'm not saying any of these is correct, I'm just trying to go with the argument over here. We'll arrive at some of the takeaways later on, right? So that's the question. So UTS, does it depend on fiber diameter? So all of you are unanimous that it's a no? Anybody feel it's a yes? No, right? Everybody feels it's not. Yeah. Okay, so which means that let's move from a qualitative question to a graph. Okay, graphical representation of that. Same question, exact question that I asked at the end of the last slide. I am asking again. I am plotting versus fiber diameter on the x-axis, the ultimate tensile strength on the y-axis. So I'm not changing the material, as I said, and you said only the force changes, force at which failure occurs changes. The stress at which it fails should not change, right? So in other words, how should this particular curve look like?
We're saying UTS is constant.
Yeah. Right. So it's parallel to the x-axis, whatever the value of that UTS is, right? So that's what you would expect, right? It's the election season. Tomorrow we're getting the results for the Indian elections. November you'd be knowing your American president. In fact, 65 countries are going for election this year. So it's a massive thing for the whole world. So here let's have a vote for the trend, okay? So even though you've already Nafisa said that it's parallel to the x-axis, let's try to look at some options here, because what's voting without options, right? So the first option is monotonically increasing, okay? A is that you start with a certain value of UTS. As you increase the fiber diameter, it goes up. So this is just speculation. We're not saying anything is right or wrong here. We're just trying to loudly think about it and try to explore what could be the truth. Okay, this is what Nafis talked about, choice B, right? It's a constant, right? Another opposite of A would be to monotonically decrease, right? So as you keep increasing the diameter, the UTS starts decreasing in value for the same material. Okay, is it possible? And I don't know if this choice is there in the American president election or any American elections, but in India we have a choice at the bottom called nota, none of the above. So people still go to vote because that's their duty to vote, even though it's not mandatory. Nobody is going to take them to task if they don't vote. But some people just want to express that none of the candidates are suitable to represent me, so I would choose nota. So that's the choice D. Okay. There could be a choice E. D could include, for example, something which is not monotonically increasing or decreasing, but it's kind of wavy pattern. It could be increasing, become a maximum and then fall off, or it could decrease to start with, become a minimum and then again increase. Okay, so all of that is contained within D. So once again, let's try to with this new choices that we have, sometimes choices makes us more confused. Without choices we sometimes answer right, but once choices come, sometimes we tend to make our decision different. So anybody going for A?
About the monotonic, like increase and decrease.
Okay.
It can be like different shape, right?
Sure, absolutely. So I'm just bunching all of them in this. So like for example, you start with a particular value, go to maximum and then come down, right? Or you could start with a particular value, go to a minimum and then again go up, right? So, or it could be a much more wavy pattern. It could be have many local maxima and minima with one global maxima or global minima, right? So all of those possibilities I'm just lumping together into this, right?
So like ultimate tensile strength is like from each material is very specific, it's fixed, but tensile strength is on a different value, right?
No, see, ultimate tensile strength is a particular kind of strength. Okay, so there are many strengths like that. So in the same direction, so if this is the specimen that I've talked about, which I was trying to pull and get the stress at which it fails, I get UTS. Same thing, instead of pulling, if I were pushing it in, I would get UCS, ultimate compressive strength. Okay, so similarly, if I were to shear this, I will get the ultimate shear strength, right? So there are many strengths, and also as Ivan pointed out, when you go to composites, you would have different directions, different failures, etc. So we are not making all of those complications right now. We are keeping a single material. It's not a composite. We are only dealing with a fiber, one material, and we are not dealing with different directions. We are dealing only with the direction parallel to the fiber. So along that, and again, we are not going in the opposite direction of compression. We are only talking of tension. So we all agreed that UTS is a material property, right? And we said that material properties should change only with the material. If I keep the material fixed and change the shape or size, it should not change, right? Because those shape and size come under the purview of geometry, not of material, right? So anybody for A still, in spite of all this logic and arguments and support from the friends, anybody going for A? No? Okay. So, okay. So anybody for B? Of course, already Nafis voted for that. Yeah.
I think in ideal scenario.
Ah. Ideal scenario it will be B.
Ideally.
Okay. Do we live in an ideal world?
It's like, I don't know, it's how C.
C. Okay. Very interesting that you brought a new argument to it. So, Ivan, why do you think it's C? If it is C.
Well, like, because you have more fibers, and because it's like.
Okay, no, let me make the question clearer. So we're taking one single fiber. We're not taking a toe or a bunch of fibers. We're just taking a single fiber, however difficult this test might be. I'm trying to pull that fiber and all the way until it fails and getting the stress value. That is what I call as UTS, right?
How exactly do you increase the
the manufacturing process. For example, some fibers are made by extrusion, like your toothpaste. When you press it out, how the toothpaste comes out. So like that, if I get the fiber made through an extrusion process, I can keep the hole of that nozzle different, and for each diameter of that hole I get different diameter fibers. Okay, but the material that I'm pushing through is the same. Is the same carbon in terms of its crystalline structure, whatever, everything is the same. So I'm just trying to push it out. I'm not saying this is the way carbon fibers are made, but I'm just trying to oversimplify things just for the sake of this question, right? So what we are trying to do is to make fibers of different diameters, all in this range of a few microns, let's say 1 micron, 2 micron, 10 microns, 100 microns, etc. So we would just want to say make a bunch of fibers and test each one of them, right? So then we want to know whether it will depend. So most of you said it's B, but you brought in a possibility in the real world, not ideal world. It could be C. So why do you think it could be C?
Potential errors in manufacturing, maybe if you use more material.
Okay.
Yeah, some internal issues.
Very, very interesting point. So you're saying that as you go for larger diameters, it's a larger area that you're dealing with and more probability of manufacturing defects. Yeah. Okay. Good. Yeah. Anything else? So this is a very, very important point both of you brought out, Anay and Ivan first. So let's see. So those are the three choices. Then what about D? Could it be anything else than these three?
I guess like it could decrease in a different way. If it were to decrease,
Mhm.
it could increase like
Exponential.
Sure, sure.
Well, it'd be
Yeah, but essentially we're saying that nowhere does it start going the other way around. So that's what monotonic means. It's essentially, if it's decreasing, it's only decreasing. In that case, if it's increasing, it's only increasing, right? So how fast it increases, like what you're saying, exponentially, etc., that's fine. But within that, so exponential is also included in that. Exponentially increasing or exponentially decreasing is also included in A and C.
There could be like a point at which the diameter is the strongest. It's like at incredibly small.
Mhm.
I don't know. I feel like there's like probably a point.
Very good, very good. So you're saying that I cannot decrease the fiber diameter continuously all the way to zero, right? So you're saying eventually it becomes a point, right? So let's say if it's a carbon fiber, what is the smallest you can go to? Right. So it's typical size of the atom, right? So I cannot have this origin as 0, 0, right? So if I have also, I cannot probably extend the thing all the way, right? Because it will not have data for very, very small diameters, smaller than typical atomic orders of magnitude, right, of that particular material. Okay. So that's why if you see, I also didn't start from the y-axis. I started somewhere a little away from the y-axis over here, right? So we don't know exactly what could happen. First of all, we could probably not even define the problem there, right? So it can be defined only when the carbon exists or any glass exists. So whatever fiber we are dealing with exists, which means there is a certain starting point, right? So is there any possibility of, as you said, yeah, exponentially increasing, decreasing is already contained in that. But is there anything else like increasing, decreasing, reaching a maximum at a particular diameter value or reaching a minimum at a particular diameter value, either local or global maxima or minima? Okay. So most of you tend to stick with B in the ideal world and C in the real world. Is that what you say? Yeah. Okay, let's see what actually happens. This is the correct answer. This is how all fibers will behave. So this is in general. The exact numbers will vary because this is a qualitative thing. We will get numbers a little for one of the examples, glass fibers. But essentially, this is what happens in reality. And what both of you said actually tallies with that manufacturing defects that you talked about, the cracks that you talked about. In particular, what we are talking about is surface level cracks. Okay, during the manufacturing and or handling, what could happen is there can be some small micro cracks that occur, and that becomes the initiation.
Before it's even put.
Exactly, before it's even put on the UTM machine, right? So now if we
That's also, in a way, has many different fibers.
Mhm.
One atom, like for carbon fiber.
Yeah.
It's like smallest as one atom,
yeah,
and then you like pair them together, the connection,
yeah, yeah.
like it's also can be different properties.
Absolutely, yeah, right. So there are a lot of issues in terms of exactly how you do the experiment, how you measure it, how reliable is the measurement, is it repeatable when you do again and again for the same material, same diameter. These are all questions, of course. We are just talking about the trend. Okay, that's what we are talking about. It's like the exit polls that we had yesterday for the Indian elections. We just get an idea of where it might be going, but we are not sure, right? So something like that. So coming back to what I was trying to say here, remember we are talking about diameter. So obviously we're talking of a circular cross section over here. So let's say this has a radius r and a length L. What is the volume of this?
Well, pi squared times L.
Okay. What about the surface area just on the curved side?
2 pi r.
Okay, so essentially it's the perimeter times the length. That's what you have, right? Now if you look at the amount of area that is exposed on the outside to because L is very large compared to R, we are not taking this area. Even if we add the areas of pi r squared on either side, it's not going to make much of a difference to this. So this is the major thing because L is so large compared to R, right? So if you take A by V, that's going to be 2 pi RL divided by pi r squared L, right? So it's independent of the length and it becomes 2 by r, right? So now you see that if you're looking at how much of, for a given volume, how much of area of exposure that is there, as you go for larger and larger diameters, what happens to the area for the same volume? So keeping V is constant, what happens to A when you go for larger diameter fibers? Area decreases, right? So that's essentially what you're talking about. And that is the area, that is the surface area on top over here, which is subjected to all these surface defects. Okay, so during the manufacturing process, there are surface defects which come because these are fairly small. The internal defects within the fiber are almost negligible, relatively speaking. There can be, but if the fiber is manufactured in an appropriate way, usually the internal defects are not much. It's only on the surface you might have a very, very small micro crack, and that's good enough for when it's subjected to a test in the UTM. At that point, the crack initiation will start from the micro crack, and it will very soon become a big crack, and total failure of the fiber can occur. So the more the area that you have for a given volume, the more the chances of the defect. Okay, because there's something called the surface defect density. So number of cracks into each of their lengths, if you add up and divide by the area, it's essentially a surface crack density. So that surface crack density is going to be much larger for larger fibers, and therefore their tendency to fail at a lower stress is more, whereas the ones make very small diameter, the area of surface area that is there is small, the number of defects are also small, and therefore the chances of going to the idealization is much more. So that's why you go there. But we have stopped at a point, and you already answered that question, that it doesn't keep increasing forever. It's not an exponential increase towards the y-axis, right? So similarly on the x-axis also, it's not going to decrease forever. It's, if you see the way I've drawn this particular curve, it's kind of becoming almost parallel to the x-axis. So closer to the y-axis, there was a larger drop. But as you go here, the drop becomes smaller and smaller for the same drop in diameter. So, and over here it becomes almost horizontal, parallel to the x-axis. In other words, there's no change in the UTS with the fiber diameter. So many of when you said that answer which is constant parallel to the x-axis earlier, you were right if you are talking about only this region of the spectrum, right? And those of you who are talking about this drop, yes, you are right too, right? So it's just a question of what is this range of diameters that I take. If I take very small diameters, you will see a sharp drop because of a sharp sharp increase in the surface defects, right? Whereas once you go here, you get what is known as the bulk material. You don't longer have the advantage of it being a fiber geometry, okay? It just becomes a rod, right? So you're just having an axial rod which you're trying to apply tension to and trying to measure that has a certain bending stiffness now. It has therefore other kinds of applications, but it does not bode well purely for a tensile kind of a application because the stress at which it fails has come down so drastically, right? So what happens over here? Again, as you said, it cannot increase forever. It has to stop at a particular point, which is dictated by the atomic size. First of all, the size is determined from that, and then the value of UTS at that point is determined by the interatomic strength at that. Whatever is the bond strength over there depends on the chemistry of that particular material. It could be a polymer fiber, then it's essentially the strength of the polymer chains that you have, how much they have straightened out, how much still you can continue to pull on them. So that those things determine it. If it's a crystalline structure like a metal or a ceramic, etc., like carbon or graphite even more, so then you tend to talk about the interatomic cohesive bond strength, etc. So now let's take a specific example over here. We'll talk about the glass fiber, okay, a particular glass fiber. I'm not sure exactly which glass fiber it is, we could to check, S glass or E glass, but one of the glasses, right? So now you see I've continued that curve all the way to the x-axis. So essentially talking about very, very small diameters, not exactly going to zero, but you're talking of the dimension which is of the order of the atomic dimensions. So then it extrapolates over there. It's not possible to test usually over there, but it extrapolates to the cohesive strength between two adjacent layers of atoms along the length of the fiber, right? Then on the other hand, this direction, it extrapolates to a horizontal line which is equal to the bulk strength of glass. You know, if you take a bulk glass, it's not that strong as a glass fiber is, right? But what you were talking about earlier is in terms of the force. Yes, force is the stress multiplied by the cross-sectional area, and therefore if you are increasing the cross-sectional area, you will increase. That is valid only in this range where the UTS remains a constant. You're just going on multiplying by larger and larger diameter rods, all rods, not fibers. So then, yes, what you're saying is right, that the stress at which failure occurs remains the same, but the force at which the failure occurs will increase because the area is increasing, right? Because force is equal to stress times the area, right? On the other hand, when you're going here, you both are changing. UTS is also changing, your area is also changing because diameter is changing. But this drop is much, much more steeper than the change in area that is happening over here, okay? And in any case, we are interested only in this UTS. But going back to what we were talking about, there is an impact of the geometry on the material in certain realms of it. So in other words, it is a material property, you're right, but when you're talking of very small dimensions, just like Newtonian mechanics fails at very small length scales quantum mechanics, and it fails at very large speeds, relativistic mechanics, right? We are not even talking of that. Within the parallel of the Newtonian mechanics itself, size effects are there, okay? And they can affect material properties, okay? So we have to be a little careful when we say these two are completely divorced from each other, that is structures geometry and the structures material properties. There are certain length scales, especially the smaller length scales, where there can be an interaction between the geometry and the material that you should be aware of, okay? So the fiber geometry's hardness implies that there's a much larger UTS. What we have plotted is UTS, but the same thing holds for E also for different reasons for any given material, but the logic is pretty much the same, that the root cause, the culprit is the surface defect, right? More surface defect means lesser inferior properties, which is what happens with larger fiber diameter, and therefore drop in UTS, drop in E as well. Yeah, I think one thing here. Yeah, so as I said, this is for glass, but the kind of trend is similar for other materials like carbon fiber or Kevlar fiber, etc. Of course, the actual physics or chemistry that is used to explain becomes slightly different in terms of the bond strengths between atoms in one case or molecules in the other case, between chains of the monomers as part of the polymer in some other case, etc. Right? Now, let's go to the reason for that. As we said, it's the lower probability of failure inducing surface cracks which are generated not only during fabrication but handling also. Remember, you are trying to take whatever has come to us from the manufacturer, we are trying to put it onto a UTM which is capable of handling such small diameter specimen, and then you are trying to fix the grips. All of this is a ripe situation for handling induced defects. Okay, so not only fabrication induced defects but handling induced defects can also give you completely erroneous results, so you have to be just careful of all of those things. But the end result is that once you go for larger and larger fiber diameters, larger and larger number of surface defects, and therefore a drop in the properties that you desire, namely Young's modulus and the UTS. Okay, so that answers for us the question of why fibers, because we know that when you have a fiber, especially typical diameters that are there for glass fiber or carbon fibers are around order of 10 microns, which means that you have at least about 4 GPa. That is what you can get. Even though the theoretical limit is 11 GPa for glass, you can't achieve that usually. You will achieve about 4. If you try to go as close to that as possible from the current state of the art in manufacturing, you get what are known as whiskers. Whisker is a word used for mustache also. Whisker is a word used for the lowest diameter in the industry. It's used for the lowest diameter you can get of a particular material. So it's when you say aluminium whisker, for example, essentially it's the smallest diameter aluminium fiber that you can get, etc. Right? So similar with glass fiber, etc. So, but you are getting at least of the similar order of magnitude. You are getting a 4 instead of 11, which is much more than 0.17, which is the bulk strength of glass. Okay, so if you take 4 by 0.17, you see such a large ratio that is there about 20 times. Or if you take 11 by 0.17, about 60-70 times is what you're looking at. So that's larger difference that is possible. So always the tendency in the materials industry is not only to go for better and better precursors, better and better manufacturing processes, but also go for smaller and smaller diameter fibers. You might bunch a large number of small diameter fibers into a toe, which is a bunch of fibers, right? That is fine. That toe can be of any standard dimension that you typically deal with commercially. But each fiber in that toe, if it is of a smaller dimension, than more number of fibers of smaller dimension, that's always better than larger number of fibers of smaller diameter even within this range, because you see the drop is quite steep, especially close to the y-axis. Okay, now let's look at Y matrices. That's the second main component of the composite. We said We answered why fiber, now we want to understand why matrix. So any takers on this? What are the main reasons you think you need a matrix in a composite? So let me clarify. Yeah, matrix, many times we might confuse with the mathematics definition of a matrix, which is essentially an